A very good morning to all of you. Maybe some of you might be just wondering why this fellow is coming at 3 o'clock and wishing us good morning. The reason is, whatever you say, good morning and good afternoon, everything, if you don't have a watch on your hand or maybe some clock in front of you, is depending on the light outside. So where the sun is and where exactly sun is going towards. So that's how it defines a day or time. Exactly the same way, the first human, he's touched with the science. Particularly, it can be easily said that it is astronomy and astrophysics. So as soon as he came out of the cave million years back and he saw towards the sky, so he saw some twinkling and bright things in the sky. So that's when he started wondering what they are and where they are coming from, where will they go in the daytime and etc. So that's how begins astronomy and astrophysics. Initially, astronomy and astrophysics, astronomy particularly was for defining the time. So later on, people started taking it in different ways. And when they started wondering what they are and how they are moving, then they moved on to find out what they are made out of and other things. We'll be um, they are talking about that in the later slides. So, as I mentioned, the human eye view of the sky is dominated by nearby stars. So, you may be wondering how many stars may be there in the sky because almost everybody thinks that it is innumerable, means you cannot count them. But actually, it is around 2,600 stars depending on the place and this one how dark the place is and how good your eyesight is. Based on that, it can be anywhere around 2,600. And if you take the whole day, assuming that you are seeing the sky, say over 2 seasons, then it can go to totally. It might go to some 5,000 to 5,200 stars. So that's all you can see with the naked eye. And for millennia, astronomical investigations has been conducted only with naked eye and in the visible band. So you are all aware of about electromagnetic spectrum. It goes from gamma rays to radio and includes visible, UV, infrared, and microwave radiation. And cosmic ray objects is seen to be radiate over the entire electromagnetic spectrum. That's one of the best things. Unfortunately, our view is restricted to the only a very small fraction of this bandwidth that we call it as visible band. Again, that visible band is subdivided into 7 colors. You are all aware of Vib Gayar, that is the colors of rainbow. And what we can see the cosmos through our naked eye is only this tiny window. So all the others we are unable to see with our naked eye. So for most of part of the astronomical study, the study was limited to this visible band as humans were using only eyes for any of these observations or deductions. So here is my observation techniques for space science. That is my topic today. So I would like to, I will be touching upon the basic tools used for observations, ground based, and why not ground based, why we need to go to space, and what we can accomplish by using these observational techniques. And I'll touch upon few of the observatories which are working in space and ground also. So here on the, I don't know, I can't point out. So you can actually see there is a flute-like thing on the left top most of the slide. That is actually a telescope. That's the first telescope used by Galileo, and before that Hampshire. Okay, so that is a 2-inch telescope. After that, Galileo started improvising that. That came in the second one. This is the first time Galileo is showing a use of telescope to the noblemen at that time. So below that is India's best observatory as of today, called Himalayan Chandra Observatory. It has a 2.4 meter optical telescope, and the site is so good that there are multitude of observatories and observation facilities which are coming up there. ISRO is also planning to set up 2 observational facilities there. One to study the debris, that is the space debris. Second one is to study the cosmos in terahertz. So below that is a biggest telescope, which is almost like from the ground. So that actually, and next to that is Astrosat, which is a space-based observatory. It is ISRO's first space-based observatory dedicated for astronomy. So, as I mentioned earlier, the first detector or a sensor anybody could use or have used is our eye. So eye can be split into iris, pupil, and sclera. So out of these things, the pupil, the dark portion in the middle, is the one which are transparent and which allows the photons to enter the eye. Hence, it dictates what is the faintness we can see, or what is the faintest object we can see. So our eye we can think of as a very small telescope. So its light collecting power is controlled by its lens, that is its iris, whose diameter usually varies from 2 mm to 8 mm. So suppose you may have just observed that whenever you go to a movie little late, once the movie is started and all the dark lights are switched off, then you might have uh, experienced that you are unable to see anything inside because you are coming from outside, which is a bright spot, to the dark side, and then after some few minutes, so you can actually see the people sitting there. So that clearly shows that your eye is getting adapted. The pupil size is getting increased, that is, it is getting dilated. When it is 8 mm, that is the highest dilation, usually typical highest dilation. At that time, you can clearly see because just compare. So if it is 2 mm, the area of the pupil is around 4 square mm, whereas 8 mm, it is 64. It's almost 16 times more. So that's why you can see fainter and fainter objects. And you can also change the focus. See, you can our eye has a fantastic ability to focus very close as few inches to few millions of kilometers away. Okay, so it can also act as a fantastic telescope with a very long focal length. And finally, using this 8 mm telescope, several thousands of stars from a dark star site can be seen. Okay, and the angular resolution can also be increased by actually using both the eyes. So what is observational astronomy? From our live sensor, let's come to actual sensors. So astronomy gathers almost all of its information from the light, which is emitted by the astrophysical sources. When I say light, it's not just a white light, it is the entire electromagnetic spectrum. We'll come to that again. So the first question asked by anybody who looked at the sky is, how bright are these twinkling points in the sky? So when you say this, how bright to visible to our eye is the easiest one to find out. That we call it as magnitude. And if we actually, if I take it such that how bright with angular resolution, that is, if I take an extended object at the edges, how bright it is, at the center, how bright it is, and at south, how bright it is, north, how bright it is. So this defines what is called as positional astronomy. And instead of space, if you say that wavelength, I think you are all familiar with the concept of wavelength. So I'm not going to detail into that. So if you split that light into multiple wave bands or wavelength bands, so then each one, how bright it is, will give spectrum. So forget about the position or wavelength, just go with time, then it gives a light curve. It actually tells us how it is varying. The simplest thing is if I observe moon over a month and every day it keeps on reducing in its brightness, right? That's because of phases. That's a different issue. It's not intrinsic, but even then it is actually reducing. So if you plot time on the x-axis and the y-axis total brightness of moon, then you can clearly see that it repeats every month. So that's what is we call it as light curve. So finally, another major observation technique is polarization. So when you take a single photon, there is no meaning of polarization. But if you make all the photons follow one particular angle or particular direction, the photons movement, then we call it as polarization. It's like telling the people who are just crossing some signal, okay, they might be randomly crossing. Some 10 people will be coming from going from this side to that side, and other people might be coming from that side to this side. And in Bangalore, even other people will be coming from the vehicle roads also. Okay, but if you consider a marathon, so all of them will start moving, running towards only in one direction. Huh? Then you can say that they are polarized. Okay, I think this gives you some idea about what polarization is. So entire astronomy is basically only these four. One, how the brightness varies over the space, how the brightness of a source varies over spectrum, means wavelength, and how it changes with time, or what are its polarization states. So that is astronomy. So how do we actually get all these four information? A particular starting with we use telescopes because, as I mentioned, our eye can be maximum 8 mm. So if you want to look for fainter and fainter objects, you have to use higher and higher collecting area, which is not possible with the eye. So you go for artificial collecting area, that is either lenses or nowadays mirrors. So then comes photometry. Photometry is to see how many photons you are getting from a target. So how they vary over it, wavelength is spectroscopy, as I mentioned, polarimetry. Interferometry is a beautiful concept, very, very interesting concept. Uh, See, whenever you are assume that you are making a telescope, okay, the maximum size you can make is in a few meters because glass has to be cooled and you have to make it like a shape, give a shape and everything. So if you want to resolve any object, two close by objects, the resolution power depends on the size of the lens. So just for example, if it's 1 meter, then lambda by d is the diameter, gives you the resolution of that. Now what if you want to observe finer and finer details? You have to increase the d because wavelength is fixed. Now you can go for a 2 meter, 3 meters, maximum say 4 meters or 5 meters. But beyond that, it becomes very, very tough or almost impossible to make a lens or a mirror. At that time, what you do, you want more resolution, means you, instead of making a single slab as a mirror, you make two mirrors of say 1 meter each and keep them separated by some x distance, say 5 meters. So now instead of entire 7 meters, the resolution will be the total distance between the two. That is, now d is the distance, which can be anything. So this is typically mainly used in radio astronomy. So it's interferometry is mostly done in radio because then whenever you bring the two telescopes, data from the two telescopes can be easily merged if it is in a higher wavelength, longer wavelength. So if it is a shorter wavelength, it will become very, very tough. So most of the places they use interferometry. See, for example, that gives you an idea. That might give you an idea. What if you keep two radio telescopes at the two far ends of Earth, then the total resolution lambda divided by d, which is now is equal to 6,000 kilometers, is very, very high, right? So that's how interferometry comes. The only problem is now you will not get aperture of the size of 6,000 kilometer radius, but you will get a sum of whatever the individual telescopes, that is radio telescope. This is about most of the times ground based. So then we have space probes. So whenever you want to study some planet or moons of other planets or our own moon, you want to send a probe. You want to go closer and study them. So that's where space probes and rovers comes into picture. So a new observation technique in astronomy is gravitational waves, which is happening now. So just to give an example, we got one gravitational wave detection few years back, and that solved multitudes of problems related to black holes and other astronomy easily with just one detection. Imagine if we start getting more and more of them. Then finally, there are particles. So you may be wondering where the particles are coming from. Particles are coming from everywhere. For example, cosmic rays are coming from all throughout the universe. Still now we don't know where exactly these cosmic rays are getting originated. Or if you have studied fusion, nuclear reactions, then you know that in a fusion, a chargeless, massless particles gets emitted, that is called as neutrinos. So in the center of our sun, the sun is also actually giving out light using fusion. So that means that whatever the number of fusion happening there, so many neutrons are getting through. So these neutrinos, since they are chargeless and massless, their reaction probability is very less. So people say that as of now, when I'm speaking, millions of neutrinos are just passing through me, and I am unable to detect them because their reaction, since they don't have a charge, so they cannot have bent by magnetic field or electric field, and they don't have mass, so they cannot transfer energy. Okay, so these are the major techniques. We'll take each of them one by one. So on the right side is one plot showing gravitational waves detected by a event sometime back. You can clearly see how the model, how the data and everything falls into picture. And I am very proud to say that whatever the chirp you are seeing in the end, this kind of chip was predicted by our own scientists from IIA. Okay, so that should actually give you a proud moment. So then I mentioned about neutrinos. So on the middle of this one, on the left are electromagnetic spectrum, which is available throughout the electromagnetic. So how do telescopes work? At a very basic level, a telescope is nothing but combination of two lenses. The effective area is given by lens maker's formula, which is given by 1 by f1 plus 1 by f2, plus and minus changes depending on the shape of the eyepiece or objective. Okay. So the magnification is given by focal length of the first divided by focal length of the second. So and the image will be upright, this is very important because initially the telescopes were used for spotting enemy ships. Okay, there you cannot actually see a ship and say inverted ship, right? You can't make out multiple things. And then for astronomy, it doesn't matter. I take a picture, I just invert it, and then I have a upright image. So I don't worry. And Galileo is the first one. Galileo is the first one to actually see. Is not a professional optician, but he used existing designs available at that time. So, and he made a telescope which is around 2 inch, and he is the first person who just looked at the sky using this telescope. That happened around 400 years back in 1610. And so this is the first telescope, and it gave a magnification around 3. That means if you have a image which is around 1 centimeter, through the telescope he could see it as 3 centimeter. But later on, whatever he made, that gave a magnification of 10 to 30. Okay, more the magnification, more merrier, because you can actually see it better. So how faint can different telescopes see? So astronomers usually classify brightness in terms of magnitude. Okay, and this magnitude scale, unfortunately, astronomers are very peculiar. So they have some peculiar ways. For them, a star which has a magnitude higher brightness has lower magnitude compared to fainter objects which has a higher magnitude. Just to give an example, our sun is -17, which is very bright, and the faintest star, what our eyes can see, that is Mizar B, what we call regular in Hindu mythology, what we call it as Arundhati, is 6th magnitude. Okay, so this is very peculiar. We have many other peculiar things. This is one of them. Okay, so this is a relative system. There is no standard 0 here. So you just compare. So one star is brighter than another star. If the magnitude difference is 10, then it is 100 times brighter. Okay, this is the easiest way to calculate that. So using this, Vega, which is in the sky, is a 0 star. The brightest star in the sky, that is Sirius A, which is also called as dark star, is -1.46. Its companion Sirius B 8.84 magnitude, which is 13,000 times fainter than Sirius A. Sorry. So this just tells you how brightness varies. Okay. Now, so how did using the telescope help Galileo? Because magnification improved ability to see fine details. So the Galileo could see 30 times better than Tycho Brahe. I told you now earlier, whatever the telescope he used is 10 to 30 times more, magnification is 10 to 30 times more. That means that Tycho Brahe is one of the best naked eye astronomers world has ever seen. But Galileo, using a telescope, could better him 30 times, by better 30 times. So his first initial telescope with an aperture of 5 centimeters enabled observation of fainter objects by about a factor of 300 than unaided eye. So he could see Jupiter's moons. He could actually see Galilean telescopes, which so these are the good things. But his telescopes had a problem. The Galilean telescopes, whatever the telescopes he actually made, had a very small field of view. It is like you just keep a pipe in front of your eye. Okay, so that field of view will be what you can look through the pipe. So if more the length of the pipe, smaller portion of the sky only you can see. So this may be good because you can actually stop all the other bright objects. Unfortunately, it will be very bad for doing survey because so you imagine you can see only 1 centimeter of the sky. Sorry, that's a wrong this thing, but just for clarification. So 1 centimeter of the sky each time, then to cover the entire sky, how much time you might take? So by just assume that instead of that, you can see sky 10 centimeters at a time. So then automatically 10 by 10, 100 times less time is required to see the entire sky. So this is what I meant by very small field of view. How small it is? So to see the moon from one end to the another end, full moon, it needed at least 3 pointings. So 1/3 of the moon only he could see with his telescope, and it is very tedious. But with this, he did wonderful work. So he found that Venus has phases similar to moon, which actually helped or what should I say? Not justify. What should I say? Clarify that sun earth is not the center of the universe. Actually it is sun. Okay, and also he detected satellites of Jupiter which are named after Galileo. In his honor they are called as Galilean satellites. 4 of them he could see. So as I mentioned, he saw Jupiter, moons of Jupiter, phases of moon, okay, and craters and mountains on the moon. So he found that moon looks very similar to Earth, and that clearly showed that heavenly realm is not a perfect one. Heavenly realm means in the mythology. So then he also observed sunspots, means spots on sun. Then again another problem, and he found that using sunspots he could actually found that sun is rotating, actually spinning. So these observations, phases of moon, sun is rotating, and all other things gave a proof that Copernicus was right, that Earth is not the center of the universe. To explain what are all these observations, then sun has to be the center of more universe, means our planet. Okay, assume that this is solar system. Earlier it was our solar system was thought of as entire universe. So sun is the center of the universe and earth actually goes around it. But because of the religious things at that time, so he has to hide this. But this was known to most of the astronomers already, but they were also little hesitant to come out. So coming to naked eye observations, we normally call it as stargazing. When I say naked eye observations, it's not just by observing through naked eye, either using eyes or telescopes or even binoculars. When I say naked eye observations, because we are not using any other sensor other than our eye. So just by looking at sky using our eyes alone gives a very wide field of view, almost like 180 degrees coverage we can get. So this is very important, or this is using this, you can actually see moons and planets clearly, or fast extended over large area. For example, if you see if you actually want to observe meteor shower, the meteors can come from any part of the sky and very fast. So if you use a telescope which is a very narrow field of view, by the time somebody shouts, "Oh, there is a meteor shower," and you move your telescope there, it would have gone. So naked eye is the best for that one, and so it gives it. You can see the extended observation. For example, our Milky Way. If you see a part of the Milky Way using a telescope, it will look like very bright, but very this one. So you will not get the complete picture, right? So that's why naked eye observation still holds lot of benefit, not benefit even this one. Okay, so for extended objects, Milky Way, for example, Milky Way or constellations or zodiac are so wide that you may not be able to use telescope. But the cons. So the problem is our eye is capable of integrating only 1/20th of a second. How do you know this? And where do you see this? Whenever you go to watch a movie, immediately the entire movie is based on this concept that our eye cannot retain anything for more than 1/20th of a second. So if something is moving faster than 1/20th of a second, or if it anything you are moving say 20 frames per second, automatically it sees that as a moving object, not as a static, even though static things. Okay. So because of this limit, even if you keep on observing some sky, part of a sky for more than an hour or some long time, it will not help you in detecting fainter objects, because after every 1/20th of a second you have that will go off. So it is limited only to brighter objects, and also it depends on the observer. So I might have some power and I might have a capability to see one magnitude, but the other person need not have the same thing. So comparison will be very tough. And also limited archive value. See, for example, I say that I saw this object in this particular direction in this field, and everything will depend on how I perceived it, not how I saw that. Okay, other person at the same time, from same place might have seen it differently. So because of this, it will be very tough to actually use older data for any deductions. But invention of photography changed this a lot. So this advent of photography dramatically increased the capability of telescopes. So just keeping a photo camera at the focus of a telescope, so people now could see much fainter objects because they can integrate it for hours together. Okay, not only this, our eyes are capable of seeing only visible light, but photographic film could actually see in ultraviolet and infrared also. See, I was telling now electromagnetic spectrum spreads over a very long wavelength, but we are unable able to see only a portion, tiny window of that. Whereas now with the ultraviolet, with the photography, we have ultraviolet and infrared also. So then, because we could actually look longer, I'm really sorry. We could split the visible, see, even for the visible thing in different filters and get atomic spectra. So that's another important thing that photography has helped us. So on the right side, you can see the first picture taken by Andrew Common, who's an amateur. So of Orion Nebula in 1883, this is the first time anybody could see fainter stars not visible to naked eye. Okay, so just to give an example, continuing on this, so Hubble observed a very small portion of a sky for continuously 11 days. So it's almost like a million seconds. And with this, can you imagine a very tiny fraction of the field of view actually has shown that each dot there is a galaxy, not even a star, it's a galaxy. If you can see here, each of these dots is a galaxy. And the faintest of them is billion times fainter than whatever our eye can see. And they have even seen light from billions of light years away. Okay, so but James Webb Telescope has improved on that. Wherever that Hubble has seen 10,000 galaxies, now the same place with the same amount of integration, James Webb has seen 100 times better. Can you see the left and right? Left is from Hubble and right is from James Webb. You can see how many more information we can get from James Webb Telescope. So James Webb Telescope is really an engineering marvel, not only for Americans or anybody. It's, you can say that it's a human engineering marvel. Okay, so you should all read about what are the things, what are the kind of technologies went into James Webb Telescope, and you will be enamored by that. Okay, so what happened till now with the naked eye observations with the telescope, not a sensor? So many questions are asked and answered also. One of them is Earth the center of the universe? No. It is found out that it is not Earth, it is Sun, which is the center of the Earth, the center of the universe. So we could actually find out how far are the stars. And using their spectra, for example, from Sun, you might have heard about Fraunhofer lines and others, we could actually finally found out what these twinkling points in the sky are made of, mostly hydrogen, helium. And then we could actually say whether solar system is at the center of the galaxy. This is the first time we have actually could see something beyond our solar system. And is there more than one galaxy? Yes, there are many galaxies. For example, M51, millions and millions other galaxies. So then we could also answer, did the universe have a beginning? By actually detecting cosmic microwave background. So we could actually finally say that yes, this light is the reminder of whatever the light emitted in the Big Bang, and hence Big Bang is the most plausible way of starting the universe. And the next question we are asking is, are there other planets outside our solar system? We have, yes, we have discovered many of them. Actually, the number is more than 5,000 now. So there are planets not just in our solar system, outside also. So many questions are answered, but there are many more questions yet to be answered, okay, which could not happen from using ground-based observatories. So then we have to go to space. But why space? Space is one of the worst areas where you would like to be. It has extreme conditions, both temperature, and it is one of the best vacuums. So for example, the vacuum is such that people say that if you take 1 meters cube area, volume of space, you'll see maximum one or two some molecules or atoms. So the vacuum is such a best vacuum there. On Earth, we could never achieve this kind of vacuum. And then temperature is extreme. During the night time, because there is no atmosphere, it can go to -100. And during the daytime, again, because there is no atmosphere, it can go to +80 to 100. So, and each way it varies whenever you are looking at sun and you are looking away from our sun. So it will keep on cycling. Whatever you carry or whatever you make, it has to withstand these kind of variations every hour, every day, every year, so long. And it is very, very expensive. See, this is the Himalayan Chandra telescope, where Indian Institute of Astrophysics has constructed a 2.4-meter telescope at the cost of 20 crore rupees. So till now I have mentioned multiple times Hubble Space Telescope. That is also made out of very close to the same size, 2.3-meter telescope. But its cost is 400 million, or approximately 2000 crore. Okay, almost 100 times more costlier than equivalent telescope on ground. And also time taken is also almost 4 to 5 times more than whatever the time it took for HCT. And then radiation. I mentioned earlier that we do study particles, and these particles are nothing but very, very high energetic charge particles or cosmic rays or whatever it is. So whatever you send up, it has to withstand the effects of these radiation. With all these difficulties, why do you want to go to space? Okay, before answering that, let me take up this. You are all aware of this picture. This is the first picture taken by Rontgen of a person, not a skeleton. So with this photo, he could clearly see a key bunch and other things, whatever he is carrying. So this paved it was a miracle in the field of medicine, because till then, if there is anything wrong, any broken bones or anything, it was impossible to identify how it is, but X-ray paved this. So not just visible, X-rays can add another dimension for our information. It can provide one more information, which can actually make it look much complete. Okay. Similarly, I already mentioned this. The electromagnetic spectrum varies from radio to gamma ray. What if we have access to all of this? So how do we get the access? So this is the electromagnetic spectrum. Assume that a cosmic source is actually emitting electromagnetic spectrum from gamma rays to radio. Unfortunately, only a very small portion, which coincidentally, what our eyes are capable of seeing reaches Earth. That is the visible part. A very little bit of infrared. If you go say above few kilometers or in a plane, our radio waves will also reach ground. Luckily, that's how we can actually we have most of our communication is based on this. Okay, if radio was also cut off, then our communication we would have taken a completely different route. And none of the most of the high energy is do not reach Earth's surface. It's a boon for us, because as you are aware of that, if you are exposed to UV or X-rays or gamma rays, it actually brings lots of medical problems like cancer and other problems, skin problems. So it's a boon. But since astronomers do not have access to this, sitting on the ground, it is a pain for astronomers. But why multi-wavelength? Why not only optical? I gave an example of X-rays, how X-rays can provide you some more information than what visible light provides. Similarly, almost all of you are familiar with this story. The story of four blind men asked to describe an elephant. So one guy said, who touched the trunk, he said that it looks like an anaconda. Another guy touched legs and said pillar. Another guy touched the body and said that it's like a ball. So like this, each one described the elephant differently. One said that it's a fan who touched its ear. Now, who is right and who is wrong? So almost all of them are right? Because with whatever the limited knowledge they have, they describe whatever they have described is correct. But to get the complete picture of the elephant, you need to combine all the four together. Okay, this is not only in India, this is a very famous fable in almost all parts of the world. So, but this is just a story. Why do astronomers want to believe in a story? So this is, you are all aware, is the picture of our sun taken in visible. So you can see spots, some spots there. It's not spots on my computer terminal. It's actually real spots. So can you see those spots? One on the left. So people have thought that, okay, these spots are because the temperature is slightly lower there. So once the temperature is lower, okay, they emit radiation to the power T to the power of 4 times 4 to the power of the temperature. So the lower the temperature, the flux will be less, and hence it looks darker than the other one. Fine, very good. We understand that. But then came the problem. The same thing holds in the infrared region also. On the left top is infrared, but below that is in radio. There's slightly problem. Looks like wherever it was darker now, but now it is brighter in radio. If you come to UV and X-rays, UV on the top right and the X-rays in the top bottom right, you can clearly see that it almost looks like the negative. So wherever earlier dark spots were there are now very bright. Other brighter places are very dark. So that clearly shows that it cannot be black body radiation, because black body radiation, as we know, it goes as T to the power of 4. But we said that in the optical, the temperature is less. But how can it be brighter in UV? Now, that clearly shows that this is not a black body temperature and something else is happening. So just by looking our sun in different wavelengths, we could actually get more information about our sun than by observing with visible light. So when you actually plot sun in X-rays over the entire cycle, you can see that whenever there is a spot, it is bright in X-rays and it varies throughout the 11-year cycle. I'll leave that as a homework for you to study sun's 11-year cycle. So this is about sun. There is a very famous object called crab pulsar. So this is a neutron star rotating very fast, so fast that 1 by 33 seconds. Okay, I'm not going to go in details. If you see that in radio, it simply looks like some steam, just a steam. But infrared, it gives a completely different picture. Optical gives some knots, but it's also not giving a picture. Actual neutron star is seen in X-rays, where you can see it looks like a top. So to get the full information of this, you have to combine all of them. Just by looking in one wavelength wouldn't have given you the nature of this particular object. Okay, so you all agree now that it is very important to study sky in high energies. But why optical and visible? It reaches Earth, right? That is given by, that is because of something called as seeing. So what is seeing? See, turbulence. See, if you just see outside your window, the wind is nothing but atmosphere is moving. So because of this movement of the atmosphere, the photons coming from the source, they will start dancing around. Because of this dancing, it will not give you a single point, it will be spread out. So you will never get a particularly focused image. The left one is the ground-based image and the right one is from Hubble. This is just because, not only because, seeing. Okay, because of that you are missing out a lot of information because it is getting blurred out. The left on the top right is the best picture taken by one of the biggest or the largest telescopes, ground-based telescopes, whereas the same taken with Hubble on the right. Now you can easily judge that even for visible, going above atmosphere helps us a lot in actually getting clearer image. And also in the morning time, you see that sun, morning and evening time, sun will be reddish in color. This is because the higher frequency, say for example, blue and other, are more absorbed in the atmosphere. It happens in all the wavelengths. So the sun will look actually less brighter because of the atmosphere. So by going above the atmosphere, we can even see fainter objects. So these are the two reasons why we need the. So because of these reasons, for a large part of the spectrum, space science has moved to space. So now we know that space is the final frontier, and we do mainly two types of studies. In situ means at the place. These are useful for nearby bodies, for example, planets in our solar system, moons, our own moon, and space weather, atmosphere, topography of the planets, and particles, and remote observations which are done by from a distance. So with this, entire cosmos is available for us, and since it is coming for far off, so it is mainly limited to electromagnetic radiation and recently gravitational waves. So in situ studies, as I mentioned, you can study particles, magnetic field, X-ray fluorescence, sample studies from planets, moons, and asteroids. So this is an example whatever our Chandrayaan has accomplished. So because you have already heard multiple talks about the moon, I'll just skip. I just want to mention here that our Chandrayaan 1 is the first mission which showed the presence of water and hydroxyl on moon. It is so important, in fact, that the US, which went to moon almost 70 years back, has completely left that field. But because the detection of water and moon has reinvigorated the lunar program of US, and it has started with the L cross. Now it is going to Artemis and it continues. I'm sure you have all heard of Artemis and others, so I'm not going to go there. So I just want to mention particles. Chandrayaan also carried another important one payload called class, which is capable of actually studying electrons. So it found that whenever Chandrayaan is moving through along with moon in magneto tail, so during full moon where where there will be it will be passing through the magneto tail, so they found burst of electrons, saying the and they could measure the energies. So the best example for in situ analysis or in situ studies is Parker Solar Probe. It mainly carried four instruments. One is instrument for science investigation of sun, ISIS. Fields experiment is studying the field, that is electric and magnetic field. And Whisper wide field imager for solar probe. Sweep solar wind electrons, alphas and proton investigation. Okay, I just want to tell a joke here. Okay, with the permission of the organizers. See, sometime back somebody mentioned that okay, one country went into moon, they landed in moon. So immediately the some other country's leader got up and said that, oh, what about them? We will land on sun. Okay, somebody said that sir, sun is very hot. So how will you land on sun? Then we will land on in the night. But now the joke is actually becoming a reality. Parker probe is the first man-made object which is going to touch sun. When I say it's touch sun, it will not go and touch the surface, but it will go very close where it will enter into the corona and study the corona in situ. Okay, so Parker solar probe, as I mentioned, carries four. So fields antenna 4 is going to study electric fields, and fields magnetometers will study magnetic field. ISIS suit will study energetic particles, both electrons, protons, and helium ions. So sweep will be studying slow moving, that is from the solar wind, charge particles, and like this. So it's going to do lot of in situ studies of sun. Okay, Whisper at the same time will be taking the images of corona and the sun, so which will help in identifying the origin of these particles and how they are moving and other important details. And since it will be very close to sun, just 100 the distance from the sun and earth, so it is going to give us much clearer images. So after the in situ analysis, we come to remote studies, photometry, spectroscopy, polarimetry, and interferometry. So start with photometry or imaging. So this is an image taken with UVIT and compared to galaxy image. So this shows the distribution of stars and the light and everything, and it will help us in studying galaxies. And these multiple colors are because this image is a superimposition of multiple filters. Then why do we need spectrum? I just told you that. So when we are talking about sun, the dark spots are because the temperature is low, and the bright spots because it goes as T to the power of 4. This we call it as black body radiation. That is on the right side image. Okay, if a body is any body which is having temperature more than 0, if it will be emitting radiation like this, which looks like a black body radiation on the right. Okay, instead of that, if that body is not emitting because of its temperature, but because of its bremsstrahlung, that is stopping radiation. Suddenly, the charge particles is stopped. Then the spectrum will look like on the left. Bottom one, if the charges by emission radiation is coming from charge particles which is spinning around some magnetic field, then that will look like almost like a straight line. So just by looking at this, we can say what might be happening at the origin, that is at the cosmic source. So this is one of the supernova remnant. With this is a 60 onboard astrosat data. So Singh et al. Has found that there are multiple lines in that particular say supernova remnant. So that clearly shows that these elements are present in that supernova. Again, so Chandra kind of detectors can give very high resolution images, spectra in X-rays. So with that, I could actually detect all the elements in that one, iron, neon, and all sort of elements. And with the ratios of these lines, I could actually define the density and I could measure what is the amount of these elements which are provided available there. So with spectra, we can get lot of information. So then comes spectrum. Here also, this is earlier it is a line spectrum called as line spectrum where you could see lines. But astrosat carries certain payloads which do not have the capability of actually resolving these lines, but they give continuum spectrum. This continuum can also define what is the process that whatever I talked earlier, na, black body or Bremsstrahlung or something, or the combination of any of these. And add to this timing. So timing means how the time is changing, means light curve is changing with time. So I'm sorry, I think I missed that plot. I misplaced the plot. Sorry. So then comes polarization. As I mentioned earlier, so polarization is the measure of what fraction of the photons electromagnetic this one is moving, that vector is moving in which direction. If all of them are moving exactly in one direction, it's called as 100% polarization, and the ratio defines how much it is polarized. So what is the use of polarization? See, just assume that you have some light falling on a big something which is reflecting it. It can be some matter or something. So this reflection adds polarization to that. So by studying the polarization signature, you can actually say what is the size of that object and what are the kinds. Like if it is a magnetic field, for example, synchrotron radiation is highly polarized. So just by looking at the polarization signature, you can say whether there is a magnetic field or not. If it is there, how much it is. So like this, we can detect, discover, or we can actually identify many things about the target by studying polarization. And by combining all the four, photometry and spectra, timing and polarization, we can get much more information. These like the four blind men actually like trying to explain how the elephant looks. Now with these four different ways, we are trying to explain what the source might be. So this is a very nice concept by URSC from ISRO. This is called as spectropolarimetry of habitable planet Earth. This is a way to see if we want to discover life on any other exoplanets, how we can do that with a polarimetry, and they want to prove using the Earth as the sample now. Okay, looking at the Earth, how its polarization signature is and how its spectral signature is, combining these two, they would like to um, select planets which are capable of holding life. Okay, this is a very nice experiment. It is actually on its way to moon on board Chandrayaan 3. It just left Earth today and it is traveling towards moon. So after this, there is a very interesting thing. So whenever you go to a doctor, the doctor will first take his stethoscope and ask you to breathe and cough. Why is he doing that? Because just by vibrations, listening the change in vibration or the sound inside, he can actually find out what might be happening inside. Whether the people say now it is completely filled with water or something. Okay, whatever it is, that medical things will not talk. But whatever the light, whatever we see from sun or stars or any other thing, most of that light is coming from it's the outer surface, that is the photosphere. Now, how do we actually peek inside? It's almost impossible to see inside. So the only way what we can do is like like a doctor, we take a stethoscope and study the star. Now the star can actually change its size. It can breathe. Okay, using this we can actually study what is happening inside. On the video, whatever you saw just now, these are called as solar 5 minutes oscillation. On top of the sun, it is not constant. It will be actually some of them going inside, some of them are coming outside like this. It will be oscillating. By studying this, we can actually probe deeper and deeper of the star. So with this only, we could actually identify that the convecting zone and radiative zone are separated by something called tachocline. And if we can actually detect what is called as G mode oscillations, this is called as P mode oscillations, which are because of sound waves. And if there are G mode oscillations, we can almost touch the core and find out about the sun. and not only for sun, other stars also. This we call it as helioseismology. So this shows various ways of a star showing oscillations. Some of them can be radial. Entire star can be changing in size, grow and come down, grow and come down. Some of them can be of different L values. So based on higher the L and higher will be the nodes which are going in and coming out. Sun, you have seen that there are millions of those nodes. This is not only sun. So the same thing applied to stars is called as astroseismology. So this using this astroseismology, we can actually identify multiple things. For example, the rotation of a star. If a star is actually oscillating in one particular frequency, because of the rotation, this results in what is called as beating. So the frequency will be split into frequency nu plus omega and nu minus omega, and there will be harmonics. Okay, just by seeing that, okay, what is the difference between these two frequencies, we can clearly find out what is the rotational speed of a star. So this is a very easy, good thing. Na? So like this, we can do multiple things with seismology called as astroseismology. So there are multiple, and for this astroseismology to work on, we should not have any breaks in the observations. So to continuously observe, it's not possible, because if I am observing sun, I can observe sun only during daytime, but in the night time it will not be visible to us. So for this, people have come up with a coordinated observations where once I stop, once for me sun is going down, other person can take up. This is called as GONG, Global Oscillation Network Group. India is also part of that. Similarly, not for sun, for other stars, there are multiple coordinate observations. One of them is called as WET, Whole Earth Telescope. So with this, we can have 24 hours coverage of this one. Now, Aditya do not has to have these things, because Aditya L1, which is going to be observing sun and which is going to be launched soon from ISRO, is going to be looking at sun continuously 24 hours because of its best vantage point L1. Really sorry, I missed out. I should have put vantage points, but you please take it up that L1, from L1 it can continuously stare at sun, so there will not be any break, and with that helioseismology can get a very good boost. So with this, to conclude, there are several observation techniques: ground-based or space-based, in situ or remote, high energy particles, neutrinos, cosmic rays, electromagnetic waves, gravitational waves, eda. So why we do this? To answer fundamental questions like how did everything begin? What are stars made up of? And finally, are we alone in the universe? Okay. So few answered questions, many more remain, and the quest continues. Okay. So thank you.